Hello students and welcome back to Chemistry A. I'm Ms. Sleight and today we're going to be talking about the families of the periodic table. First off, you're going to want to pull out that new periodic table that you were given with the arrows on it and grab some coloring utensils because we are going to color code the main groups of the periodic table. So here's kind of our key. In white we have our other nonmetals. The dark teal is the alkali metals. Notice how although hydrogen is in the same column as the alkali metals, it's not included as part of the group because it is actually a nonmetal. Hydrogen itself doesn't belong to any specific group on the periodic table because it has really unique properties that doesn't make it fit in one particular spot. It also happens to be the most abundant element in the universe. The teal-colored elements are our alkaline earth metals. The pink, which makes up almost everything in the D block, are our transition metals. The green at the bottom, which also includes lanthanum and actinium, are the rare earth elements, or also called the inner transition metals. In gray, we have our other metals. The yellow stair step are our metalloids. Metalloids are elements that have characteristics of both metals and nonmetals. And everything to the left of the metalloids is a metal, which means most of the elements on the periodic table are metals. Everything to the right of the metalloids are nonmetals. And you can see in white, again, we have our other nonmetals. In red, we have a very important group because of their reactivity, the halogens. And then in black, we have another important group due to their non-reactivity, the noble gases. So take a moment to pause the video so that you can color code your periodic table appropriately. Now let's talk a little bit more in depth about the periodic table. It's really a fascinating device because of the number of things it can tell us about elements just based on how they're positioned in here. And the story of how Dmitri Mendeleev created our first periodic table is really interesting. And if you want to learn more about it, I've linked a video about him and the periodic table to the website, and you can check that out if you're interested. In last chapter, we talked a lot about how an element's row number, or an element's period, that's what we call the rows on the periodic table, periods, how those numbers corresponded to the highest energy level occupied by an element's electrons. In this chapter, we're going to talk a lot about the significance of the column number. Columns on the periodic table are called groups or families because elements within the same column share very similar physical properties. You're also going to see that they share very similar electron configurations because the arrangement of an element's electrons is related to its properties. Let's start by talking about Group 1A. Group 1A, if you notice, their electron configurations all end with one electron in an s orbital. They're known as the alkali metals, and they are very soft, highly reactive metals, so soft that you can cut them with a butter knife. But they are also violently reactive with water to the point where you have to store them in oil so that they don't react with water vapor in the air. They all have one valence electron and form +1 ions. Now we're going to take a look at a little video that shows you just how reactive each of these metals is with water.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Well, that was certainly an interesting one. Now let's look at our next group, Group 2A. Group 2A, all of these elements' electron configurations end with 2 electrons in an s orbital. They are known as the alkaline earth metals. They're all silver-colored and soft metals. They are reactive, but not quite as reactive as the alkali metals. They all have just 2 valence electrons and form positive 2 ions. Next, let's look at Group 3A, also numbered as Group 13. Group 3A, all of these elements have 2 electrons in an s orbital and 1 in their outermost p orbital. They are known as the boron group, named for the first element in the group. In nature, they're most often found as oxides, and they each have 3 valence electrons and form positive 3 ions. Next up, let's look at Group 5A, also numbered as 15. Group 5A, all of their electron configurations end in an s2 and a p3. They are the nitrogen group, also named for the top element in their group. Historically, they've also been called the pnictogens, and this group includes nonmetals, metalloids, and metals. Each of the elements have 5 valence electrons, and they will form negative 3 ions. Next, let's look at Group 6A, also numbered as 16. Group 6A, their electron configurations all have an s2 and a p4 involved in their outermost electrons. They are called the oxygen group, historically also referred to as the chalcogens. This group includes nonmetals and metalloids. Each element has 6 valence electrons, and they form negative 2 ions. Next up, we have Group 7A, also numbered as 17. Group 7A are called the halogens, and these are highly reactive nonmetal elements that each have 7 valence electrons and form negative 1 ions. Now let's take a little look at a video that examines some of the properties of these elements and also lets you see them in their natural state.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colorless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the colored vapors, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid, or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2, and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of a pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all four of these reactions are white solids, and they're all trihalides. Al3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
Next up, we have group 8A, also labeled as 18. Group 8A are called the noble gases, or sometimes called the inert gases, because these nonmetals are completely non-reactive. Naturally, they will not react with any other elements, which is why they were some of the last elements to be discovered. They all have full valence shells, meaning that their orbitals all contain the maximum number of electrons. With the exception of helium, that means they each have 8 valence electrons, and they do not form ions, again, because all of their orbitals are naturally full. Next up, let's talk about our D block elements. The D block elements are called transition metals. Transition metals are known for their high melting and boiling points. They're also extremely hard and can form multiple ions. So most of these elements can form anywhere from a +1 to a +6 ion. Lastly, let's talk about our F block elements, including lanthanum and actinium. Our F block elements are referred to as inner transition metals, and they're often broken up into 2 categories, or 2 subgroups, the lanthanides and the actinides. They're also sometimes called the rare earth metals. Not necessarily because they are rare or hard to find. These metals are fairly abundant in the Earth's crust, but they're found in very low concentrations, which makes it difficult and not cost-effective to mine them. However, they are used a lot in electronics and high-performance magnets. And those are the main families or groups of the periodic table. Again, make sure you color code your periodic table to represent the main groups that we have listed here if you haven't done so already. And have a great rest of your day.